Hello, this is Group 5. Our group has decided to investigate reservoir computing's potential in text generation. We have seen recurrent neural networks in class, but one that we have encountered in other courses is reservoir computing, also known as echo state networks. There are a handful of papers employing them in NLP, but it seems research has slowed down in previous years. In the next slide, we will continue a graphic that should clear things up, but we keep in mind that ESNs contain a fully connected input layer and a very sparsely connected recurrent reservoir of nodes. These two layers are randomly initialized and are untrainable. The only thing we can train is a fully connected linear output layer. So here we have the promised graphic. A main advantage of ESN as opposed to other language model is how few trainable parameters there are. The number of neurons in the reservoir multiplied by the size of the output vector. In our case, that is just the reservoir size times the word embedding vector length. Next, Anders will continue on why we use reservoir computers.
So, why do we want to use reservoir computing? To understand this, let's take a look at the Lorentz equation, which we can see on the upper right picture. This system has a nested set of update rules, which makes the system very hard to predict. In order to understand why this system is so hard to predict, let's give a visual example. Assume we have a set of data points in the outer trajectory. We assume that this follows a logical pattern that any deep learning model would be able to learn. If we, on the other hand, assume that we have a set of data points in the chaotic system, the trajectory will be more complicated to estimate. This is where the reservoir computing comes into play, since it has been proven to have great ability to predict time series generated by chaotic dynamics. The essence of reservoir computing is to take a low-dimensional input and expand it into many, often thousands or 10,000s of dimensions. This high-dimensional encoding can then be easily decoded by a linear layer to produce accurate predictions. When we think about language, a sequence of text can take many different trajectories, but we usually have an idea of where it's going. If I say, he went to the restaurant to, you would probably guess that the next sequence would be eat or meet friends or something like that. But depending on what was said before that sequence, you might suspect something entirely different. Subliminal hints or vibes gives us an intuition that is hard to capture with machine learning. The next sequence could very well be something surprisingly like, he went to the restaurant to start a fire outbreak, if what was said previously had a subliminal hint underpinning this. In this case, we drew parallels between chaotic system and language. Where state changes appear seemingly randomly, are these state changes deterministic, and can they be predicted? If language behaves like a chaotic system, our hypothesis is that the reservoir computer will capture them.
We chose this dataset because news stories don't read like novels. There's much more discontinuity because the goal of a news story is to get information across, not to tell a story. These are some stories included in the dataset. Because of Zipf's law, which applies even to n-grams, using a simple token to int mapping, even if we scale this value down, makes it difficult on the output layer. Since our reservoir nodes use a hyperbolic tangent activation function, we mapped each token to a sample drawn from a normal distribution according to its frequency in the dataset. In other words, frequent tokens lie close to zero, while uncommon ones lie on the tails. We also experimented with multi-dimensional word embeddings, but we weren't able to generate text using this. Finding the most similar word embedding to a generated vector introduces problems and doesn't produce anything worth showing, especially as the size of the word embedding increases. The reservoir's internal states are initialized to 0, and the weights from one reservoir node to another are initialized from -0.1 to 0.1 with 5% probability and otherwise 0. At each time step, the map values of 5 words are fed into a randomly initialized fully connected layer and then into the reservoir. These values are multiplied by a leaky rate and summed with the product of each node's previous internal state, the reservoir's weight matrix, and 1 minus the leaky rate. After a transient to make the reservoir sufficiently non-zero, these values are then multiplied by a trainable, fully connected layer to produce a single output value. And if we are predicting, then the closest word corresponding to that value is generated and placed at the end of the next input sequence. With the leaky rate, the internal memory of the reservoir decays exponentially. In a sense, the model is similar to LSTM in that the reservoir memory is akin to long-term memory, and the 5-word sequence input is akin to short-term memory. And these are some samples we generated. As you can see, it's not so good. In the third example, we can see that it at least wanted to keep talking about food. We got our training MSE to about 0.01, but perhaps a longer training set would help. A problem we identified is that since common words correspond to map values close to 0, these are the values the model is biased to predict. When it begins predicting these values, its inputs are also close to 0, resulting in repeated predictions of the same or similar typically stop words. With the models parallel to LSTM networks, we decided to compare it to 1.
My teammates have explained about the reservoir computing model, which has been used for generating the text data. So we just got an idea of how about we can test the result that we have generated using the reservoir computing model with another recurrent neural network model. So we just got an idea of testing, building another model like LSTM model, like a simple LSTM model, and getting output from the LSTM model. How the text has been generated, and we can how compare which is the best model for both for when comparing both the methods. So this LSTM model is also a family of recurrent neural network, and this LSTM model has been used for like many tasks, like a predicting task, music generation, text generation also. But why they are using this LSTM instead of RNN is like due to the problem called vanishing gradients. So recurrent neural network generally have one problem like a vanishing gradient. So when that is vanishing gradient is when the gradient of the loss function decay exponentially over the time, and because of this the models forgetting the information, the time series information for a long terms. Like for example, it's kind of forgetting the very past information to predict the new one. So because of these stuff, the LSTM model and introduced, and this LSTM model overcome this problem by using a memory cell. So this memory cell has several gates like an input gate, forgot gate, and update gate. So these gates are like an input gate, update gate decides which information that can be passed from the hidden state to the next state, and the forgot gate is like a what kind of information can be passed from previous state. So like whether we need to remember the information of previous state, or we need to forget the information of previous states. So further, we kind of use the simple LSTM model, which can be identical like a convolutional neural network model. So here we have a 2-layer LSTM model. So the first layer is LSTM layer. So this LSTM layer dimension is equal to its network input size. So we have used the parameters called the input shape here, which tell the network about the shape of the data that we are going to train. Further, it is a dropout layer which is used for regularization. So this can be done at training to prevent the overfitting as it update a fraction of input to 0. So here we use like 0.2 as a optimal dropout value. Further, there's another LSTM layer, and lastly we have a fully connected dense layer. Which connect to every single node corresponding to the output node. So the dimension of the last layer in our project shows the number of unique output that is being required. So lastly, the activation function layer, which also determines the activation function used to calculate the desired output. So here in our case, we used softmax optimization. So we use the categorical cross entropy and process the iteration through this as every output belonging to one class. But here we are dealing with at least 84 classes as characters. So as far as the optimizer is concerned, we are trying out a couple of optimizer, and we settled down with the Adam optimizer as it end up in giving some good results. Further, here we can see some result that has been generated by the LSTM model. So initially we just seeded like similar to the last like ESN layer. So we just begin the predicting with some seeds, and we just feedback our prediction as an input. So here we can see the LSTM model has been trying to predict some new words when comparing with like ESN model, maybe a similar. So initially it can predict the new words, and after some certain time it's kind of predicting the same word. So this is maybe due to the fact that it's not remembering most of the words from the past data. And here we use like 30 epochs and 128 as a batch size. So we believe like even if we could have used more epoch, trained the model for more epoch and more batch size, the output could have become a more better, I think so. So as a conclusion, ESN may not be the best tool, I would say, but Using high dimensional embedding requires an impractical large reservoir, as well as a low dimension embedding will take a even a lot of reservoirs. So we cannot just prove language is chaotic, but it could be fun to apply one of these to BERT embedding, but that could require a massive impractical reservoir. So hope you could have enjoyed our presentation. Thanks for watching.